Ma'am, can you join the meeting? Oh, I'm searching for your name. Yeah. Okay. Yeah, sure. So the participants, we are ready for the next session. Now we are moving to our next session. It's titled Demystifying the Quantum Machine Learning Applications, Challenges and Limitations. So it's my pleasure to introduce our next resource person, Dr. Anupama Namburu. She is an associate professor in the School of Engineering at JNU, Jawaharlal Nehru University, New Delhi. She has a diverse academic and industry background, having previously served as an associate professor at AP University and Acharya Nagarjuna University. And also, she has an industry experience as a senior software engineer at Wipro Technologies. Dr. Anupama ma'am holds a PhD from JNTU Kakinada and MTech from Andhra University. And her research interest includes medical image segmentation, soft computing techniques, artificial intelligence, data science, web and mobile application development, generative AI, and quantum computing. She has authored more than 30 publications in SCI and Scopus Index journals and conferences. And she owns 6 patents, and she also completed the 3 international visits as part of her research endeavors. Her achievements include receiving all the prestigious award like Feather in My Cap Award at Wipro Technologies and Best Research Paper Award, Best Technical Club Award, Best Academician Award, and she was honored with Above and Beyond Award with BITAP and many research awards. And she's also the fellow of Computer Science Research Council USA. Her exceptional blend of academic research and industry experience positions make her as a leader in her field and consistently contributing to advancements in computer science and technology. Thank you so much, ma'am, for accepting our invitation and being here today. Over to you.
Thank you, Shilpa. Yeah, just a second. I'll just share my presentation. Okay, so is that visible?
Yes, ma'am.
Okay, so very good evening, one and all. So probably it's been delayed, but then I have taken this concept because, see, quantum computing itself is a huge, complex task. So with this presentation, probably I'll try to make it much easier to understand what is like quantum computing, and then how the machine learning algorithms currently are being developed in this field. Okay, so that is my idea. So the outline of the presentation would be like I'll be covering a paradigm shift of how machine learning is happening, and then need of quantum computing and the basic qubits and gates. With this, how the machine learning is evolving. So that's the reason I'll just quickly give some basics of qubits and gates, which we will be using in the further slides to build up the machine learning algorithms, and then we'll take up some queries at the end. So basically, supervised machine learning, you might have already learned, right? You have the labels predefined, and then you have the data set. The model will try to map the data set with the predefined labels, and then it gives you the prediction. So supervised is like you have a pre-class data, right? And in unsupervised learning, there is no prior data. So the data will look in among themselves, and then they will group among themselves. So they will match among themselves how they are similar or how they are dissimilar, and the model will try to analyze those similarity, and then it will group. Okay, so there is no prior data, which is basically the unsupervised learning. And then the era which is currently is the generative machine learning, where you can use a text to generate an image, or to generate a video, or to generate an audio, or you can use an audio to generate an image. So it's like vice versa. You can use any kind of prompt to generate any kind of output. So, and then current research is also moving ahead with the multimodal uh, uh, I mean, LLMs, which is like you can use multiple modalities of data. Like you can combine the text, the audio, the features as well. You can use images, so lots of things together, and then produce the data. So now, if you take the medical field, right now, it's like there are different things which are in different ways. So now people want is like you can input CT, you can have a doctor prescription, you can have a data analysis out of it, combine all those together, and whether we can give out a very fruitful medical analysis or the diagnosis out of it. So the multimodal is currently in research, which is like a parallel way going ahead. So in upcoming years, most of the research would be in multimodal LLMs. And coming to quantum machine learning, this is like basically using qubits or circuit. This is also kind of generative machine learning. But the thing here is, see, in a classical generative model, you will pass numbers, right? And then you will be using weights, and then you will do some additions, or you will do some multiplication with the weights, and then you will use activation functions to activate that neuron and send it to the next layer. So probably all the deep learnings where you use lots of layers, lots of kernels, or the filters you can say, with which you will activate something and produce the output. But in the quantum machine learning, it is basically like you are having the qubits. So it's not just the numbers. Now the qubits are passed as the input. And here, all these will be like the superpositions or the entanglements or the inferences which interference which will be included in the model. So here the qubits will be like mostly using some kind of rotations and entanglements or some quantum gates in order to produce the output. So don't worry at the moment. So I'll try to make you understand at the very basic level. I'll try to give you an easy way of understanding the things. Okay. Um, So that's it. So here basically the qubits will be passing through, and here the entanglements or the quantum gates will be used in order to produce the output. So this is what is the idea. And when you look into the quantum machine learning, so probably this is a standard notation. Basically, we have two things. One is classical data and the quantum data. And again, you have two ways of executing the system, which is like you have classical computer, you have a quantum computer. So basically, right now, classical data, classical computing is what till now we were doing, right? And now the quantum data on a classical computer, and as well as a classical data on a quantum computer and a quantum data on a classical computer. So these are the two things which are currently under the research. But mostly is like now what we are looking is at the quantum machine learning is we want to apply our classical data, zeros and ones, on the quantum machine. So and we want to map that. So in order to map that, you have to convert your classical data to the qubits. So to do that, there is no straightforward way, but you are just using the simulators right now in order to put your data in the form of qubits and store it on the quantum machines and then execute it. So the simulators are providing you the environment, but right now, I mean, in India, we don't have that. But I suggest is like when I share this PPT, I want you to go and see the quantum, Google's quantum AI lab. Okay, so this is, you can see actually how a qubit is designed, and basically it's like a hairline structure which is embedded into the into the devices. That's the reason the quantum machines are in vertical in shape. Okay, so a news yesterday it was, and it's released today. It's like Google has designed a quantum chip. So basically this quantum chip could do a task in less than 5 minutes, which was like the supercomputers might take 10 power 25 years, which is beyond the age of the universe. So the quantum machines are achieving so much. So this is also like what the benchmark test they have used and what level of the quantum machines they have used is like with the Google. So it's a what to say, debating kind of, but still they have released it saying that 10 to the power of 25 years of computation is replaced within just less than 5 minutes. So this is amazing, right? So that's the reason world is moving towards the quantum computing. Let me see that. See, in classical bits, like when the switch is on, it's 1, and when it is off, it's 0. And if you can think about qubit as a movable switch which can range between 0 and 1. So these are called cats because between 0 and 1, there is excitement which is happening between them. You can think it as a sphere. It's not just 0 and 1. The excitement is between 0 and 1. 0 and 1 can be together. So 0 can be of 70%, 1 can be of 30%, or like 1 can be 50%, 0 can be 50%. So these kind of different excitements are represented basically in a block sphere. So this is how. So the 0 if it is off state, and 1 it's an on state, and you in this sphere, this is the excitement where the values can range between 0 and 1. So you can just assume that the value can be anywhere in this. So this is what is a qubit means. So the qubits between 0 and 1, the cats indicates that there is an excitement between these two. Okay, so you can refer this block sphere how it works, but out of time I'll not go for it. So basically, why do you need a qubit? See, when we have zeros and ones, we have like a computation power of 2n. So 2 into 1, 2 times, either 0 or 1. But with the qubit, you have a computation power of 2 to the power of n. So let's say you have 0. So 0 to the power of n, 2 to the power of n computations you can do. So it is becoming more and more powerful. So you are getting a more computational space. That's the reason a lot of data can be put in and executed, and then you have a computational capabilities increased with the quantum computing. So basically, when we think about quantum, so three things will be there: superpositioning, entanglement, and interface. So superpositioning is, we have a 0 and we have a 1. We can superposition both together. So it means, let's say the basic standard example that will be explained is a cat example. The cat can be alive, at the same time it can be also dead. So it's something like superpositioning of the two things. And entanglement is something like, we'll see these things in the above. So, and coming to the application, this also I'll not cover much, because I think most of the trainers have already have given this, why you need quantum and all those things. Okay. So now coming to the superposition. So this is a fundamental concept that is used in quantum computing. So in classical computing, only we have zeros and ones, but the qubit is a combination of zeros and ones at the same time. So this state of qubit is known as superpositioning, and these can be represented in waveform, in block sphere, in vector space. So in different spaces you can represent. So basically, this is a superpositioning where alpha 1 and alpha 2 will represent how much percentage the two items are superposition. So this alpha 1 can be a probability, how much it is 0, and alpha 2 is a probability how much it can be 1. So as these two are complex numbers, that's the reason the value of squares is always 1. So this is the basic representation of a brass eye, which is the wave representation of a qubit. Okay, so when I told you like block sphere, so this is an off state and this is an on state. So when you represent in a vector space or in a qubit representation, so off is here 1, it means it's off, and blue here is it's 0. But when you come down blue is on, so that's why blue is 1 and the red is 0. Okay, so this is the probability at which zeroth probability is full, 100%, and whereas the on probability is 0%. So because we are representing each qubit with, let's say this is alpha 1 and this is alpha 2, so the probability of being off is 100%, the probability of on is 0. Okay, and when you see at the bottom, the probability of off is 0, whereas the probability of on is 1%. Similarly, the excitations can be in any of this location in the sphere, right? So if you take this position will be like 0.5, which is a positive direction. And if you see on the other side, it would be a negative direction. So 0.5, 0.5, and 0.25, 0.75. So based on the probabilities you can think of. Let's say there is a point at this location where my cursor is. What would be the probabilities of it? Can you just think of it? Anyone? If this is the location at which my point is, so it would be half of this, right? So it would be, the above off would be 0.5, but it is minus 0.5 and 0.5. So it is plus or minus 1, which is nothing but an I. So it is I 0.5. So this is how a blob sphere is represented, and this is how the qubit will be living in any of these situations. Okay. So that's the reason when the quantum machines run on qubit, usually there is a sine wave, which indicates that there is an excitement which is happening. So definitely go to see the Google AI lab in your YouTube. So you will clearly understand how quantums, qubits, how they visualize. So they have given a very good example on that. Okay. So this is how it represents, but because of the mathematical notation, it is just it's a square root. So square root of 0.75, which is nothing but in qubits, we represent it with 1 by root 2, which is 2 number of bits, because we are using two values, 1 and 0. If it is 3 bits, we will go ahead with using 1 by root 8, because 2 to the power of 3, we can have 1 by root 8 programming. So this is how usually a block sphere represent a qubit in the excitement state. Okay. So the wave function, let's say if you take 0.75 percentage of this value and 0.25 percentage of the one value. So this is how the blob sphere representation of a qubit is. Okay, so if you want to represent a 3-bit qubit with equal superposition, so it's equal ratios. That's the reason 1 by root 8, because 2 to the power of 3. So you will have like this. Let's say you have 4 qubit, 1 by 2 to the power root 2 to the power of 4. So like that, the evolution or the representation of the qubit will go ahead. Okay, so once you understand the qubit, the qubits can be represented in different notations. One is with the blob sphere, you know this, and arrows. So up is like for off and down is for on. And then the superpositioning, where both have the equal probabilities. So 0.5, 0.5, and this is like on is 75% and off is 25, and this is 0 and 1. So if you see the vector representation 1, 0, if you see this representation 0, 1. So whenever you are working with the matrices, whenever it is like off state, you have to represent with 1, 0, and whenever it is on state, you have to represent with 0 or 1. So in wave function, it is represented in this format. So if it is off, it is 0. If it is on, it is 1. And then the superpositioning both together is like 0.5 and 0.5. And this is like the probabilities with which it is like 75% of 1 and 0.25 of 0. So this is how the representations look like. Okay. So now, but when we come to the output, okay, so basically during the computation, it has so much of excitation. But when we see it or when we measure it, so basically we will see only these values. So at the end, you will see only 2 values, because it cannot be in all the positions at the same time when you measure. So when you do a measure, the values will be at some percentage, so being like 70% of off state and 30% of on state. So this is what is the measure. So during the computation, the qubits will be in an excited state. But then once you measure or once you see the outcome will be only one, either this or that. But during computation only, you have lot of values. Okay. And then the quantum circuit. So basically this circuit measures how much is the positive, how much is the negative, or the on state. So based on that, the circuits basically are used to display the output or by measuring the output. Okay, so this is what the circuit is. So when we talk about quantum gates, so these are also one of the important things, because we use this. So that's the reason I'm just giving you a brief of it. So this is a simple AND gate, but once you see outside, it's only one output. The thing is that in quantum, when you are doing with quantum gates, the inputs and outputs should be same, because the quantum circuit should be reversible. Because when we are using quantum gates, we say that lots of interference would be there, lots of noise would be there. So we have to design a gate or a circuit in such a manner, if you produce some output, it should able to reverse itself, so that there is no error in it. So in order to prove, in order to acquire that state, basically the quantum circuits are like reversible. So that's the reason you cannot use this standard gates on the qubit because in the standard gates you have only one output. So this 3 information is lost. So that's the reason you have to go with the quantum gates. So in classical gate, you have only one output, whereas in quantum gates, you will have a similar how many number of inputs that you give, that many number of outputs, you will get it. Okay. So basically a simple NOT gate. If it is 0, output is 1 in classical gate. If it is 1, output is 0. So now in order to achieve this, okay, so this is the on off state. Now if you want to have an on state, so what you can do on qubits, it's basically a rotation that you can do on qubits. So this rotation is just on the y direction we are doing. So if you want to do this from this, so you can do on x direction rotation also, you will get a different notations. You can do it on a z direction also, you will get a different notation. So basically, if you want to implement a NOT gate, so Polish gate we call it in quantum. So if you want to use that, basically you will go with different notation. So basically it's a sphere as we are talking. So you can move it on y direction, you can rotate on x direction, you can rotate on z direction. So this is the math given. So basically this is a derivation that you can look into when you are in a 3D dimension. Basically, imaginary will take as y direction, x is the real part, and the z is the imaginary part. So because of the imaginary computation, you have i's here. Okay, so basically when theta is pi, in that case, the values of rotation, because I'm flipping from off state to on state, so I'm flipping it on a y direction. So that's the reason when I compute it with this, so this is a 1 0 is for off state. So when I'm multiplying it, I'll get a 0 1, which is an on state. So basically in NOT gate, we are using this Polish gate, which is rotation on y, to compute it into a negative. Even you can do it with the rotation on x direction, rotation on z direction as well. So that is one simple NOT gate, and the next gate is a quantum Hadamard gate. So basically Hadamard gate is one which will really superposition two in equal halves. So in two equal halves, in the sense, let's say I'm saying 1 0. 1 0 is the zeroth cat, which means it's an off state. So when I multiply it with the Hadamard gate, so this is a Hadamard gate which is designed. So if you are multiplying it with, so you are getting 1 by root 2, which is root 0.5, 1 by root 2, which is root 0.5. So it is an exact half positioning of 0 and 1. So this is where exact the superpositioning of 0 and 1 is happening. And now let's say you are here at this location, and now once you multiply with 0 1, so it is giving 1 by root 2 and minus 1 by root 2, which is moving towards on the left hand side, even though this is the same superpositioning, but it is on the negative side. Okay, so basically the Hadamard gate will rotate, I mean, you rotate your qubits in such a way that it will superposition them equally, or superposition them onto 1, or superposition them onto -1. So basically when we measure, so the Hadamard gate will make it either onto the positive cat or a negative cat. So this is how the Hadamard gate will be working. So this is a simple gate. So these NOT and the Hadamard gates were used for superpositioning. So the next important feature of quantum is entanglement. So entanglement is the ability of quantum to exhibit correlation between the two states, or correlation between the states within a superposition. So let's say you have two bits, let's say 0 0 0 1 1 0 1 1. So in these two cases, 0 0 are mostly correlated and 1 1 are mostly correlated. So in entanglement, what we see is the two bits, that we are measuring are mostly correlated. So that's the reason we always try to look into now further circuits where we can bring in the correlation, because in qubits there is always this kind of entanglement which is involved. So that's the reason. So let's say there is a C0 gate which is called a control NOT gate. So in this control NOT gate, basically you have two qubits. So whatever is, if whenever the control line is 1, and then the bit is inverted. So it means that, let's say 0 0, there is no change, okay, and 0 1, whenever 0 1, so the control bit is 1, right? So 1. So that's the reason the bit on A is inverted. So A bit is inverted, and 1 0, the bit on B is 0, so no inversion would be there. But when the bit on B is again 1, the A is inverted. Okay, so it is something like if you see it's a kind of X0 gate which exhibits a similar functionality 0 1 1 0, except that this thing. So you have because as we said in quantum gates you have two outputs, so that's the reason the B is also outputted, so that this can be used for the next process. So this is a C0 gate. So it has lot of advantages when we use. So basically when we use a C0 gate, okay, so what happens is if the bit on the control bit is 1, so it will just reverse the last two. So basically if the control line is 1, it will reverse the inputs. So basically the last two inputs will be reversed. So whenever you produce some outputs, though in C0 gate, the last two outputs will be inverted. So now there is also control NOT gate where it has two control bits. So whenever these two control bits are 1, then the target will be inverted. So you can refer this, whenever these two control bits are 1, this A target is reversed. Okay. So this is a controlled NOT gate. And there is also a universal reversible logic gate which is called used as NAND gate. So here also like I mean the CCN is called a NAND gate as well. Okay, so given we have understood what is C0, let's say rotations, we have understood Hadamard, right? So now I want to do an entanglement. So entanglement in the sense, even though you have 4 inputs, I want to entangle or I want to identify only these two. Like either it should be 2 off stage or either it should be 2 on stage, because each bit is entangled with a correlation. So I want to find out the most correlated, like the off states and the on state. So in this case, a simple quantum circuit, basically it's like first thing is a Hadamard gate. So the qubit 1, so let's say qubit 1 has 1 and 0 and the qubit 2 has 1 and 0. So I want to use, so I want to produce this output, right? So entanglement, so either 2 up states or 2 down states. So this is the one which I want to acquire. So if I want to acquire this, so this is a simple circuit. So when we apply Hadamard, so Hadamard is when you pass 0, it gives equal superpositioning. So 1 and 0, it indicates it's an off state. So you will get, when you apply this Hadamard gate on this, you will get root 0.5 and 0.5 equal superpositioning. And when qubit 2, you're not applying anything. So it comes as it is 1 and 0. Now, when these two are passed to the C0 gate, so basically this is a dot product. So multiply 0.5 with 1, it is 0.5, 0.5 with 0, it's 0, and 0.5 with 0.5, I mean 0.5 with 1, 0.5. So you got this logic. So when we apply this C0, what's happening? The last two bits will be inverted. So when we invert this thing, so if you see here, the values of 0.5 comes to this and 0 comes to this. So now you are acquiring a 2-bit entanglement here with a simple Hadamard gate and a C0 gate. So this is what you will be doing most of the time when you are working with the qubits. And let's say this is another circuit with which you can mathematically convert whenever you see in a circuit like YY, entanglement in Y direction, XX, entanglement on X. So basically ZZ. So if you see only one parameter on X, it means it's a rotation. So you have to understand the notations of the circuit. So whenever you pass these two, I mean, with this matrix, you can directly get this entanglement. So this is also another way. These two are not the ways. You can design your own circuit and you can produce a paper. So because the quantum is in evolving state, so the research is at the basic level. So you can still work on your own ways in which how you can build on. Okay, so basically bell state. So 0 and 1, it's easy. Simple Hadamard gate, you can equally do the positions, right? 0 0.5, 0 0.5. And for 2 bits, 2-bit entanglement, root 0.5, root 0.5, you have used Hadamard and C0. So this is also fine. But if you want entanglement with 3 bits, so all 3 up or all 3 down, you want to generate this circuit. So it's a bit hard. And even harder is like you want to produce 4-bit. It's harder. So now with the understandings of this, you have to build up a circuit which can learn and which can actually entangle the qubits. So 3 bits, 4 bits. So people have tried doing it on qubits. So the idea here is like whenever if it is a single qubit, right? So the superpositioning was easy by using a Hadamard. So simply if you apply a Hadamard gate, 1 by root 2 of 0 you will get, which is 0 0.5 root 0 0.5 of 0 and root 0 0.5 of 1 get. So if it is 2 qubits, so if it is 2 qubits, you have to use an entanglement with Hadamard gate and a C0 gate, then you are able to acquire this thing, right? And if you are working with 3 bits, so you need to work on, you have to play with the angles basically. So you have to play with, if I set this angle and then combine this value or combine this value, whether we can get the entanglement or not. So this is like you need to work on, because quantum is not so easy. You need to be smart enough to understand, to apply the idea, like how you can entangle the things or how you can apply the gates, how you can rotate the angles to acquire the outputs. So this is what is the idea. So for 4 bits, you have like n number of topologies in which you can try. So this is how the thing should try and it should be produced. Okay, so one such machine learning which developed was the quantum circuit born machine. So which they wanted to find this entanglement. So first, the qubits, they have put it in the quantum computing, and then they evaluated the space and they found out this is the space. And finally, they want to acquire only these two. Like, but now this is the result. How we can acquire this entanglement? So basically, this bond machine, they have designed with an idea like we have to do some rotations, we have to do some minimization. They have came up with a one basic model. But the idea here is like they measure it, still they are getting some output. So the idea here is, so when they pass some input, okay, to the machine, so they are recording what is the output, how much probability the output is coming. So they are basically acquiring or they are training the circuit. So, I mean, once they train it, they are measuring what value is the output. So the values are between 0 to 15, so because of 4 bits. So this is the obtained model. So once they have obtained this, what they have done is, this is what we want. This is the entanglement that we want. So once we want this, they are comparing the obtained histogram with the one which we are desired. So to compare this, there have been suggestions, like they have used in their paper the KL divergence, log likelihoodness, or maximum mean discrepancies. So basically, it's a comparison of the probabilities. Okay. So based on the comparison, if the comparison is very closer or very larger, based on this, they have started updating the angles. So basically, this updation of the angles, what they did is they have used simple particle swarm optimization. So if they search the space and try to find out the best fit or the team best result, and then based on that they are giving the angles, and that angle they are updating and they will note it, and again they will compare, and again they will update the angle. So they are doing a training process until like the circuit is adjusted with the angles. So this is one publication which is made in 2019, with which the basic learning has started up, and they have actually like started executing on this. Okay, so and further, there is a research work on producing KNN with machine learning. So basically, what they did is, in basic KNN, basically you will find k nearest neighbors, and then based on the distance measure, you will be updating the centroids, right? So here, most of the KNN would be like working on the calculations of the distances. So to speed up or to parallelize the process, so they thought that, okay, shall we apply the quantum bits for measuring the Euclidean distance? So this is what is the idea that they have incorporated. So here, basically, if you want to see any inner product of two, let's say x, y is the distance that we want to find out, and in qubits, x and y distance is measured in this way, which is an inner product, which is simply a multiplication of these two things. So with this idea, what they did is like, I mean, you have different measures, but people have started work on Euclidean distance. So what they did is, to implement the Euclidean distance, they have used a swap test. So again, if you see here, you have a Hadamard gate and you have CNOT gates, and again a Hadamard gate. So this is not much difficult task. So what if you have a basic understanding of the gates, you can easily create the circuits. So this Hadamard gate. So Hadamard gate is like superpositioning of the two things. So on 0, when you apply, it is root 2 of 0 and root 2 of 1. So this is nothing but, so 0, 1 by root 2, or 1 by root 2 of 0, 1 by root 2 of 1. So whatever may be, it's the same thing. So once you apply this, okay, so you are getting the first Hadamard, when we apply, this is what we are getting. So which means that half root 2 of 0 AB and 1 of AB. So this is the expansion form that we did. And now when the control shifts to this place, so we are applying a C naught. What is C naught? Whenever the control bit is 1, you have to swap the values. So here you have to swap A and B. So when the control is 1, you are swapping the values. So 1, B and A. So you are just shifting the values. So once the shifting is done, now again a Hadamard gate is there. So once you apply Hadamard of this 0 is again 1 by root 2 of 0 and 1. So 1 by root 2 of 0 and 1 AB. And once you apply on 1, it is root 1 by 2 minus root 1 by 2, right? So that's the reason you get 0 minus 1. So 1 by 2 is common, because 1 by root 2, 1 by root 2, when it is multiplied, it is 1 by 2, right? So that's the reason you get it. And once you evaluate this, you probably end up with finding the probabilities of 0 is 1 by root 2 plus 1 by root 2 this thing, or probability of 1 would be this. So you need this. This is what is the distance measure that we need, right? So once you put it onto this side, so you are acquiring the probability of 1, or you can even do with probability of 0. So now the measure for a Euclidean distance turns out to be like this. So whatever is the measure is the distance that they are using it to compute the Euclidean distance. So whenever we use qubits, so it's a vector of distances that would come, and when you measure, you will get the output. So this this swap test, they have used it even for the k-means as well. So in the k-means algorithm also, it's like you will define 3 random centers, and from that centers you will find the Euclidean distance, and then whichever the members are similar, you will group them together, and with the groups you will find a new center. So it's always the computation of the distances. So in order to make the calculations much better, so in 2023 it's a 24 paper, so where they have used a Hadamard gate, and they have used a X rotation, and then the Hadamard gate. So here encoding, they have used amplitude encoders. Basically, when you come to quantum computation, there are different types of encoding, like basis encoding, amplitude encoding, you have wave encoding. So there are so many encoding. So amplitude is basically takes the magnitude and based on of the qubits, and then it passes. So this is a simple Euclidean distance they have designed. And further, they have even enhanced this version by adding a measure of 1 and this, and they have added an additional 0 response as an input. So with this, they have shown that they have acquired a better output. Okay, and even for direct classification of KNN, so this is a circuit they have designed up, and this is a very recent paper. So basically, if you are